Jose Solis-Ocampo, Lab 3, Black Holes and Orbits. So the introduction, the purpose of this lab is for, in a computational model, we have defined the mass of the black hole using the motion of the orbit of the star and all the forces acting upon it. And in a second experiment, we are determining the velocity of a spaceship to orbit a planet and star while calculating the forces acted upon the spaceship. And for our goal for this experiment is to demonstrate the principles of Newton's second law and see the effects of all the different forces acting on the spaceship. For some of the fundamental principles used, we use Newton's second law, which is the net force is changing based on the object's velocity, and more mass an object has, more force is needed to move it. The gravitational force, which is an attractive force between all objects that have mass or energy, and bigger mass equals bigger force. And parallel and perpendicular net forces, which the components of an object's direction of motion and trajectory when the force isn't in equilibrium. Here are some of the equations used: the average velocity formula, the two update formulas for the position and velocity that update the position and velocities of the objects in the thing, Newton's second law, and the gravitational force to acting upon an object, and the two parallel and perpendicular components which we will be using in the computational model to see the specific forces acting on an object. And here are the initial conditions for part 1 of the experiment. The system was the star and the surroundings were the black hole in space. For the seed, I used my personal Georgia Tech email, and here is some of the initial conditions. The mass of the star was given to us at the project, the gravitational constant as always, and the time interval between the input data was given. Here's some of the overview for the glow script. Here I computed the initial and final momentums for the star, and also calculated the changes in velocity and changing momentum for the star, and did it all out in order to use the Newton's second law of F net equals dp dt. And over here I calculated the specific parallel and perpendicular forces acting upon the objects. So we put the specific F nets for each and put it all into the formula. And here was the mass, the formula for the mass of the black hole, which was the magnitude of the F net times the R mag squared over the G constant times the mass of the star. And here is the code for the arrow components, and here is the results. And also, as you can see while I was watching it, there was many masses getting added up. So in order to find the correct total mass, I averaged them all up and got 1.53 times 10 to the 34 kilogram for the mass of the black hole. Part 2 initial conditions. So these were all given to us at the start, and through trial and error, I found this to be some working speeds for the ship so it wouldn't crash into the planet or the star. And here's some of the glow script code. This is the net forces acting upon the moon, including the F-grab on the moon by the planet and on the moon by the spaceship. And they're the specific forces that were acting upon the objects. And here we use the gravitational formula, G times M times little m, what we've been using, and including all the other position formulas to get the correct F nets on each object. And I did the same for finding the net force on the moon for the same as net force for finding on the spaceship as down here. And here is I used the both update formulas for Newton's second law to get the thing moving. Here's the results. And as you can see here, the spaceship is in magenta, and it is not crashing, and it is orbiting the star. And when the planet gets by, it's also the forces are acting upon it. Some possible sources of error here are incorrect initial velocities, or uncalculated outside forces, or issues in the computational model. So what if and when does it mean? Part 1, how are the net forces and parallel and perpendicular force components different from the rate of change of momentum in its parallel and perpendicular components? So the rate of change of momentum is calculated from the star's observed motion, while the net force is what caused that physical change. So for the components, the parallel changes the star speed, while the perpendicular force changes the direction of its motion. For part 2, if you wanted to predict the motion of the entire system, what would you need to include it in your computational model, and would any force be dominant? In order to predict the whole system, gravitational forces between every pair of objects must be included, including from the black hole, star, planet, and all the moon, all the forces between those, and all the forces must more or less the same, because the biggest objects will have the more dominant forces on closer objects, so not all forces will contribute equally in the system. Thank you.